welcome to our studio guests today and to fellow travelers out in cyberspace, thanks to that non-stop stream of zeros and ones. My name is Peter Gobets, co-founder of the Zero Project and moderator of the International Conference/Workshop on Zero. The Zero Project is a three-stage affair. There's a book project, an associated online event, and the in-depth research program. But today, session number 8. We welcome Thomer Gil, Secretary and Treasurer of the foundation set up to commemorate René Samson, who was not only an astute scientist, but also a talented composer of modern classical music. Thomer will say a few words about his friend, and I'd like to thank Thomer for accepting our invitation so last minute to speak about René's career as composer after briefly introducing yourself. Thomer, please take the floor.
Thank you, Peter. Thank you for giving me the opportunity to say a few words about my friend René. My name is Thomer Gil. I was, but I like to think I still am, a good friend of René for the last 25 years. I'm also a board member of the foundation that bears his name. A little quick history about René. He was born in 1948 in a Jewish Surinamese family in Paramaribo, the capital of Suriname, formerly known as Dutch Guyana, in South America. The house he grew up in was steeped in music and dance and theater and literature. From an early age, René learned to play flute and piano. He played in symphony orchestras, chamber music groups, and various bands. At age 18, René started studying chemistry at the University of Amsterdam and then at the Weizmann Institute of Science in Israel. He did his postdoc at the University of Illinois at Urbana-Champaign and subsequently at the Massachusetts Institute of Technology. After completing his degree, René worked at Shell, where he worked until his retirement. René had a son, Jeroen, who went on to become a scientist himself. And maybe we can see the first photo of René now. At all times, René dedicated his free time to music, studying flute, playing in various orchestras, and so on. I originally met René myself in a small choir where we both sang, mostly performing works written by 20th century Dutch composers. At age 40, René began composing music. He took composition lessons with various teachers, and René composed works for choir, musical theater, instrumental chamber music, and vocal chamber music. He composed roughly 100 pieces, and since 1998, his work has been performed regularly. A variety of ensembles and musicians took an interest in his work. A significant portion of the work that René composed had been commissioned by prominent Dutch and international musicians, and one of his compositions was even rewarded with an International Composition Prize. René's work was often rooted in poetry, frequently dealing with topics of loss and death, and the desire for something that is no more, for love, silence, and emptiness, the poetic and emotional equivalent of zero, if you will. But not all his work was serious. The texts he used and the music he wrote were often humorous and funny. René always had a naughty glint in his eye, and it reflects in his music. But in all cases, René took a deep interest in instrumentation. That is to say, he aimed to gain a thorough understanding of the instruments he was composing for. One musician, a baritone, described to me that René understood almost better than himself what his voice could do. He paid careful attention to the articulation of text, ensuring that lyrics remain comprehensible. And that is something that other composers frequently pay less attention to. Many of the pieces that René composed had been commissioned by professional musicians, which is a testament to the care he took to understand their instruments. Maybe we can see the second photo now. His family, his friends, and a large group of musicians were all heartbroken when René suddenly died of a heart attack on his way home, riding his bike through the park in July 2019. Many of us got together shortly thereafter in an effort to document, archive, but most of all, promote his music. That effort resulted in a foundation called Stichting René Samson, the René Samson Foundation. And as part of that work for the foundation, I have the pleasure of working with many musicians that have frequently performed this music in the past and have had the pleasure of working with René personally. It will come as no surprise to any of you that they unanimously describe him as a delight to work with, modest to a fault, and always grateful for the work the musicians were willing to put in. I know that René was frequently moved to tears by their talent and dedication. A few weeks ago, the foundation and the musicians organized the first Samsoniad in which René's music was performed, to the great delight and appreciation of everyone that was there. The foundation aims to make this Samsoniad concert a yearly occurring event. On a personal note, I had the pleasure of spending endless dinners and late nights over the course of 20 plus years talking with René about all aspects of life, but especially music. Our recurring activity was to spend evenings listening to a piece of music we had agreed to in advance and then discuss it. Those discussions were frequently very technical, but René could weave together science, philosophy, history, and a love of music like nobody else. The new depths and dimensions of music appreciation I carry with me as a result of these discussions are a lifelong gift. It is no understatement to say that I loved René fiercely, and he awoke such love in many, many people. During our evenings and nights, he occasionally spoke of the Zero Project and the work he did for the organization. I'm thankful you gave me the opportunity to briefly speak about René. Thank you very much.
Thank you very much, Thomer, and all the best, of course, with the foundation. We'll follow your adventures as hopefully you will follow ours. We welcome another contributor to the Monograph on Zero book project, Professor Joseph Biello in California, who will speak on zero in modern mathematics and physics. Joe will also pay a special tribute to the late chairperson of the Zero Project, Dr. René Samson, a dear friend and colleague whose untimely death in 2019 was a great shock to family and friends. René had a large share in both the book project as well as the online event. Joe, may we first invite you to briefly introduce yourself and then pay the ode to René and then launch into your contribution to the book project, please.
My name is Joseph Biello. I'm a professor of mathematics at University of California, Davis. I in particular came to a mathematics department through physics and fluid dynamics. In the year 2012, in February of 2012, I found myself on sabbatical in Amsterdam at the CWI Amsterdam. And at that time, we were living, my family and I were living on Jacob van Lennepkade. And just walking the razor's edge of life, I happened to have a downstairs neighbor, a kindly person. And I came to get to know him, and his name was René Samson. And as all things, we get to know people slowly and then more quickly. And then, if we are fortunate, we get to know them intensely. And when we get to know them intensely, they open our minds to thinking in a way that just superficial relationships cannot. And in getting to know René, I learned that he was a former chemical engineer, and his background working at MIT in particular. And we spoke of both of our love for applied mathematics. At that time, he suggested, showed me a problem he had been working on and off. We had left several years before, and he hadn't given it much thought anymore. And I thought, I like this man. I'd like to think about what he was thinking about. And I rushed upstairs and spent a few days upstairs and came down one day and had solved his problem for him. And at that moment, it was a moment of true love between two people that I hadn't experienced in a long time. And that love was one of completely immersing oneself in the love of mathematics and in the love of shared joy for simple yet deep problems. What I learned, and I continued to collaborate with René for several years afterward over email as I had come back to California. But what I learned about this man that I truly loved at this point was that he had insights and depth that allowed him to see things and to experience things in a way that I was only beginning to acquire, and only through him could I then start to acquire that. Why am I talking about René on regarding the Zero Project? Because René was a physicist, and so he lived with mathematics in a very particular way. Those of us who experience physics and mathematics, we are dealing with mathematics at every second of our lives. We see things mathematically in ways that I've come to realize most people don't see. But René was also an artist, and through his art, he could see the world in a completely different way than I tended to see it. And the marriage of those two thought processes made his physics much richer, and I believe it made his art much richer. So I just need to share one part of René, a communication with René. I had been not working on a few problems for several months, and I had been out of touch with René. And on the 5th of July, of 2019, I wrote him. And I wrote him to write about our project, and then I shared a bit of my life with him. And he wrote back to me the most empathetic and beautiful email about the love of his life, Anneliese. And I can only share a little bit of it because it's personal. But excuse me, it is very sad. We're generally not well trained how to cope with situations of grief. Of course, we have the extra complication that we are in love. It is all very confusing to me. And all he could think about at that time was the people around him who he loved. And he signed it off. I wish you the best of luck, my buddy. Please give my love to all your sweetie pies, which were my daughters. I share this reminiscence of René with you because this man was a true scientist and a true technical man, but at the same time, he was a true humanist. And I think it is through the marriage of different thought processes that we gain deeper understanding into human nature. And the exploration of zero is really, truly an exploration into human insight into the world. So that's my little homage to René. René, after a few years of collaboration, René contacted me and said, Joe, my wonderful friend Peter has asked me to think about this Zero project, and I don't know how to think about zero. How do we think about the history of zero? And I'm like, René, I don't know about zero. And so we meditated on zero. We exchanged some emails, and we asked the question, well, we know nothing about the history of zero, but what we know is how we experience zero in our mathematics. And I thought, how does that provide a contribution to the Zero Project, the history of zero? And then I realized, and René realized, that it provides a contribution because our conceptualization of zero right now is part of the historical arc of how humankind has thought about zero through the millennia. So though I can't speak to the origin of zero, I can speak to how we conceive zero right now. And so René and I wrote a little part of the manuscript, which I would like to read to you. The reason I want to read it to you is because René and I share ideas, but in the end, it was René's writing. And because it's René's writing, it really truly reflects his insights because it weaves together his poetic nature and his scientific nature. I would just like to share a little excerpt from this for you. Kevin, can you put the triangles on for me? And then go ahead to the first Saturn photo after this. And we'll go back to the triangles in a moment. The significance of the number 0 for physics, by René Sampson and Joseph Biello. What is the significance of the number 0 for physics? At first sight, this may seem like a rather silly question. Viewing physics as a branch of applied mathematics, the latter is the business of dealing with numbers, and 0 as the origin of the real numbers. It's obvious that 0 is the alpha and the omega of physics. Take 0 away, and what's left of physics? It's like taking the oxygen out of the air and asking what's left of life on Earth. Not much, and certainly not much very exciting stuff. So, why write a paper on a subject that is so thin and worn out? Well, consider the following. In physics, as in George Orwell's famous novel Animal Farm, not all zeros are necessarily of the same standing. Some zeros may be seated higher on the Olympian mountain than others. The statement asks for elucidation. In the next section, we shall discuss the so-called conservation laws of mathematical physics. In the context of these laws, we shall demonstrate that the zeros that feature in these laws rightfully belong to the Physics Hall of Fame. They definitely have a higher standing than any other odd zero, if this crippled figure of speech can be pardoned. One qualifier must be made at this point. With the possible exception of a few remarks later, this paper only contains material that is familiar to the professional physicist, so we will be discussing it for the layperson. In our conception, I take a digression here, our conception of 0 has to do not with equilibria necessarily, but something that is deeply important in our conceptualization of the world as physicists. And this begins section 2, which is conservation laws. Natural phenomena as they present themselves to our observing eye or to our measuring equipment either seem to be seething with movement, such as the flowing of a river, the incessant movement of the clouds against the sky, the burning of trees and other organic material in a wood fire. Or they are unshakably and majestically still, like a mountain, the stars. A layperson might think that a physicist who wants to study the subject in the category seething with movement would dive headlong into the exciting business of chaos and violent upheavals. Nothing could be farther from the truth. To the layperson's astonishment, the physicist finds that the most important questions have to do with stillness. Typically, the physicist will ask the questions. First, in the midst of all this furious change, what are the things that do not change? Second, those things that do not change, what are they and how are they defined? And third, can we understand why they do not change? At this point, it is best to become concrete so that the discussion does not bleed to death in abstractions. It would be beautiful if we could give an example from a real life and blood situation, like the flowing of a river we mentioned before. For pedagogical reasons, however, it is better to take a far simpler example, something not quite as complicated as a river. Consider a pistol being fired and follow in your mind's eye the trajectory of the bullet exiting the pistol. Under real life conditions, the bullet's trajectory is not that simple, because of the influence of gravity, air, and unexpected other phenomena. To make life really, really simple, let's just assume we could somehow magically eliminate all of these other phenomena and the influence of the air molecules. And in that case, the bullet's trajectory would be perfectly straight. The bullet would neither accelerate nor decelerate from the moment it leaves the gun. It will just keep on flying at the same speed indefinitely. Things don't get sweeter and more boring than this. Now we can answer questions, the first and the second from before. The thing that does not change is the velocity of the bullet, both its direction and its magnitude. However, question 3, why does it not change, is a little bit trickier. Do we understand why it doesn't change? Truly understand? Different generations of physicists have given slightly different answers to this question. For example, Sir Isaac Newton the father of classical physics, would probably answer roughly as follows. Effects, he would say, in nature are the outcomes of causes. Without causes, no effects. By eliminating gravity and air drag, we have in fact eliminated all of the extraneous causes, hence no effects. It's not fully satisfying, though, as an explanation. There is no reason for the velocity of the bullet to ever change in this circumstance, but that's not fully satisfying. In later centuries, some scholars would adapt the wording of this argument somewhat, but the basic idea did not really change. This apparently simple-minded physical experiment is a special case of a much more general one that we mentioned before, and it describes the so-called conservation laws. In this particular case, the conservation laws tell us that something, to wit the velocity of the bullet, doesn't change as long as there are no disturbing factors, in this case forces. In physics, there are many such conservation laws, and all of these laws expressed in the mathematical formula have the form something is equal to 0, where we have written something as a general concept of what you have to understand what it means. In general, that something is a mathematical expression, but it can have a more or less complicated form. Whatever it may be, the thing that all equations expressing conservation laws have in common is the fact that the right-hand side of that equation is equal to 0. This tells us that that something does not change. It is not trivial, because that something is what is important, but its grounding in the lack of change is also important. In the case of the bullet, the physicist would say the rate of change of momentum is equal to 0. Physicists are absolutely nuts about these conservation laws. The latter are truly the cornerstones of physics. Above, we've given one particular example, the conservation of momentum. But if there are forces, we can actually generalize that example. There are a whole plethora of other physical phenomena that obey similar conservation laws. The most important among these are energy, angular momentum, and charge. These laws are always expressed in the same form as the first equation. Something is equal to 0. That does not mean there's absence of motion. It means there is exchange that comes in a balanced way. And so, to the physicist's mind, 0 is not absence, but it is balance. Now, to answer the third question, we come into the question of symmetry. And here we are looking at a picture of Saturn. And I would like to draw the reader's attention to 2, maybe 3 features of this photograph of Saturn. To the best of our eyes' approximation, that planet is spherical. It is a beautiful sphere. That's the first thing to note. The second thing to note is that the rings of Saturn orbit this planet in a beautiful plane, in a very elegant plane. And in fact, that plane is coplanar with the lines of latitude of Saturn, as you can see right there. Which leads us to our third section, symmetry. Because it is through symmetry that conservation arises, and it is through symmetry that 0 comes into play. A layperson leafing through a textbook on modern physics might be amazed how often the word symmetry is used, and she might well wonder, what is it about symmetry that so fascinates physicists? One of the reasons for her disconnect is that laymen and scientists do not assign precisely the same meaning to the word symmetry. For laymen, symmetry is a concept that has meaning exclusively in relation to forms and shapes. His face is almost perfectly symmetric on the left and right, for example. Although the physicist knows and uses this conceptual meaning as well, she tends to use the word in a rather more abstract concept. Scientists talk about symmetry, or rather about symmetrical operations, as actions that, when performed on objects, leave them unchanged. Kevin, if we can have the triangles up. By way of example, let's take an equilateral triangle on the left. Now rotate this triangle 60 degrees, or as I prefer to say, pi divided by 6 radians, around its central point. the point in the middle that is equally far removed from the three vertices. This is illustrated in the figure. And what happens to this rotation? In fact, nothing at all happens. It is returned to itself. And we can see that we're not cheating. We didn't sit on our hands instead of giving the triangle a 60-degree spin. We marked the three vertices here by a black disk, a yellow disk, and a red arrow. Comparing the first and the second large triangles in figure 1, we see that the markers executed the musical chair dance, as René would say. I can hear his voice in every word that I speak. But apart from the markers, nothing else affected this rotation. So if we imagine that there are no markers, we wouldn't be able to tell the difference between the triangle that had been left alone and the one that was rotated, or the one that was rotated twice. We call this a rotational symmetry. And in fact, this would be called a discrete symmetry in mathematics. It is the rotational symmetry of the equilateral triangle. It is discrete because there is literally one motion that can generate all the other motions. And that motion is not just a small turn, it has to be a certain minimum turn. Roughly around the time of that quantum theory knocked on the door of physics, which was shortly after 1900, physicists started to realize that there was a deep connection between symmetry and physics that needed further study. This realization did not come out of thin air. It was preceded by more than a century of feverish developments in mathematics, starting in the early 1800s. Great 19th century geniuses such as Lagrange from the 1700s to the 1800s, Abel from 1802 to 1829, and Galois from 1811 to 1832 discovered that there was a world of incredibly exciting mathematics buried in the systematic study of symmetry, such as the rotations of the triangle, but there are several more. Kevin, if you could return to one of the images of Saturn, the one on the diagonal. This activity gave birth to a new branch of mathematics called group theory. And for a long time, group theory had the reputation among physicists of being no practical use, until Eugene Wigner in the 1920s and others saw how group theory fitted into the quantum theory of atoms and molecules like a hand in a glove. Physicists who learned the trade after 1930 simply cannot imagine physics without group theory. Now, here a layperson's one-paragraph summary of what physicists actually do with group theory is going to be presented. Suppose that a molecule existed of three identical atoms that are arranged in an equilateral triangle, as shown in figure 1. As soon as the physicists know the structure of the molecule, she has an enormous amount of extra information at the tip of her fingers. She knows, for example, that the interactions between molecule and light must obey the specific dictates of the triangular symmetric group. This theory tells us what kind of spectral lines, and a spectral line is the energy emitted by those molecules, will or will not be emitted or absorbed by the molecule. In other words, the confluence of quantum mechanics and group theory leads to a marvelously rich and powerful toolbox for the practical physicist. And that comes from symmetry. And that symmetry is related to conservation. And we visualize that conservation through zero. At this point in the story, the reader may wonder if the authors have not strayed miles away from their topic of zero in physics and conservation laws. But hold on, dear reader. We will come back to our major topic, but not after we have indulged in an intermezzo. And I will continue reading just a little bit about this intermezzo because it was very important to René. And then I will leave you. Intermezzo. The life and times of Emmy Noether. In a popular treatise such as the current one, the temptation to interrupt the story with a biography of one of the main persons in our story is irresistible. If we were looking for a Hollywood-style story full of sounds and fury, our choice, without a doubt, would relate to the life of Évariste Galois, one of the main founders of group theory and modern algebra. His biography is almost beyond belief. Somebody ought to make an opera about this man. However, we will resist this temptation and choose somebody else in whose life there was considerably less gunpowder and violence, but whose biography gives us pause to consider some of the serious issues in the academic community and indeed in society in general. The person to whom we refer is Emmy Noether. She was alive from 1882 to 1935. Many renowned mathematicians and scientists, among them Einstein, have called her the most important woman in the history of mathematics. In 1915, she was invited by David Hilbert to join his group at the University of Göttingen. For those not in the know, in 1915, practically every living mathematician considered David Hilbert to be the most important person alive in mathematics. In Hilbert's group, Emmy Noether was definitely at the place to be. Although her academic output was rich and far-reaching, here we will only consider one of the many achievements. Her theorem, that is now generally known as Noether's theorem. She conceived it in 1915 and published it in 1918. Einstein, after reading the paper, wrote to Hilbert, "Yesterday I received from Miss Noether a very interesting paper on invariance. I'm impressed that such things can be understood in such a general way. The old guard at Göttingen should take some lessons from Miss Noether. She seems to know her stuff." In popular terms, the content of Noether's theorem boils down to the following. Between conservation laws and symmetries, there is close correspondence, in the sense that to each conservation law, there corresponds one specific symmetry, and to each symmetry, there corresponds a conservation. Let's try to understand this theorem in a specific case. The case of the flying bullet that moves at constant velocity in the absence of perturbing forces. In fact, I will skip this case because I'm going to take my digression from René's writing, and let's look at Saturn that I've shown you up here. The force of gravity has a symmetry to it, and the symmetry is very simple, and it's the following. If I have a mass, an infinitesimally small mass, this idealized mass, I have no sense of its shape. And therefore, if I look at it from below, from above, from any angle, it appears to be the same. And therefore, the force it exerts on the objects around it is invariant under any rotation around, any revolution around that. That is a symmetry of the gravitational force. And the consequence of that symmetry, the consequence of that symmetry is that we see that the angular momentum of any object in that force field is conserved. And the consequence of that is that Saturn rotates in the way it rotates, and all the particles in the rings around Saturn rotate in the same way. The angular momentum being an imaginary vector pointing in space perpendicular to the plane of rotation of those rings. That is the conservation of angular momentum. That arose from the symmetry in the force of gravity. And that gives us a constrained motion to those objects in the ring. That means angular momentum is constant. That means its rate of change is 0. Yet that does not mean there's nothing happening in those rings. If you were to look closely in those rings, you would see the particles moving around furiously, even bumping into one another. But they have to do that in such a way to conserve angular momentum. According to Noether, the correspondence holds for every conservation law. For energy, energy is conserved because systems are invariant in time. For angular momentum, it is rotational invariance. Noether's theorem has become one of the most important concepts in mathematical physics. Its importance cannot be overstated. And I conclude with this because this was dear to René's heart. Before returning to the main body of our discussion, let's stop for a second and ask ourselves why it is that Noether's name is known so little to the general public, yet the greats like Einstein and Hilbert are. It's hard to avoid the conclusion that this has everything to do with the fact that she was a woman. In her days, for a woman to be taken seriously, to make a career seriously, took almost superhuman effort. The prejudices of society and the obstacles to be overcome were beyond belief. Here's one more particular example, not referring to Emmy Noether, but to another eminently gifted woman, Fanny Mendelssohn. Fanny's younger brother, Felix Mendelssohn, from 1809 to 1847, became the world famous as the composer of numerous works of musical works of great genius. The Mendelssohn family was probably one of the most open and liberal group of people in Germany at their time. Like Felix, Fanny, whose life overlapped Felix's, was a huge musical talent, both as a composer and as a pianist. Nevertheless, this is what their father wrote to her in a letter in 1820. Music will perhaps become his profession, while for you it can and must be only an ornament. Although Felix was privately broadly supportive of her as a composer and a performer, he was cautious, professedly for family reasons, of her publishing her works under her own name. He wrote, "From my knowledge of Fanny, I should say that she has neither inclination nor vocation for authorship. She is too much all that a woman ought to be for this. She regulates her house and neither thinks of the public nor the musical world, nor even of music at all, until her first duties are fulfilled. Publishing would only disturb her in these, and I cannot say that I approve of it." With supporters like this, who needs adversaries? Returning to Emmy Noether, although eventually she found her place in the academic world, she had to endure tribulations which few male scientists, let alone male scientists of her stature, would have accepted. Before her appointment at Göttingen, she worked for 7 years at the University of Erlangen without pay. Once accepted at Göttingen, she did not lecture under her own name, but under Hilbert's name. Finally, in 1909, her habilitation was accepted so that she could carry the title of Privatdozent, which certainly did not do justice to her eminent academic achievements. Kevin, if you can put the picture of Saturn from the North Pole above with a hexagonal pattern. So this is a picture taken, I think, in infrared light of the North Pole of Saturn. And there's a beautiful hexagonal pattern that you just could not imagine from looking at the side. It's not very large, it's several thousand kilometers across, but not very large compared to Saturn. The point I want to make here is that the pattern that you see here arises from a conservation law, a different kind of conservation law. And the conservation law basically says that an object which we know to be called potential vorticity relates to the rotation, the wind speed, and the height of the surface of Saturn together. That is carried by each particle that is endowed with potential vorticity, and is carried, and it is not changed in the particle's trajectory. And when you write down that conservation law and you start moving particles of air or of gas around Saturn, they are constrained in what they can do. And this is one of the beautiful results of that constraint. So there is a symmetry that creates the conservation law of conservation of potential vorticity. And that conservation law creates another symmetry on this planet, which is this beautiful hexagon that we see at the top. Only a far-ranging mind like René Samson's could see the connections between the artistry and the physics and the mathematics, and therefore really have an insight into zero. And having lost him so early, I think we lost a great richness of insight that we could have brought to many other fields, in particular to my life. So with that, I close.
Thank you, Joe. Thank you, Joe. And of course, Thomer as well. It's a hard act to follow, but to attempt to connect the Zero Project to the two papers that you and René wrote, without delving into detail, let me just say that from our own studies of the origin of zero, the context, the religious, philosophical, linguistic context that likely facilitated the invention of zero, which was a historic event. It had not been around, and then suddenly it appears at some point in history, apart from the other numbers. And we're trying to find any kind of a connection to get a better idea of the profundity of zero and the difficulty of its invention. And I think what you've demonstrated, René, and you, is that zero has had a lot of manifestations and a lot of applications and a lot of use to societies across the world including in modern mathematics and physics. It's not just a historic event that ended at that time with its invention, but it went on to generate all kinds of original ideas and developments that have led to our modern world. And part of the other article that René wrote, as you remember, is, what would the world be like without zero? And he was hard pressed to try to rationalize that. But I think you've given us a good flavor of René's mentality, of the articles, of the content of the Zero Project, but also of our late chairperson of the Zero Project, who in his own very amicable way kept us on the straight and narrow. We tended to veer off in this or that direction as we pursued the project and gathered momentum by attracting a lot of scholars from across the world. We tended to, get derailed here and there, and René had a wonderful way, easygoing way of keeping us, focused on the invention of zero and all of its significance. So we do miss him greatly that way. He's also a personal friend, go back a long time. So thank you, Joe. Thank you, Thomer. Two very, very touching and eloquent homage to somebody who left much too early. He had great potential.
May I interject one thing?
Please.
Just because we don't have the discussion time so much today, but I want to add one thing, because there's something else. Although René and I discussed zero and its understanding, how we understand it now and how we use it, what I realized in thinking about zero in the way we understand it now, when we talk about physics, we don't, as physicists, we don't talk about physics as a subject. Physics for us is the world. It is the observation of the world. And when we think of mathematics, we think of sort of the categorization of that in some sense, how we simplify, conceptualize. And one of the things I realized in thinking about my friend René is that, and it took me to the time of thinking about the persons who conceptualized zero at the dawn of time, whenever there's the dawn of history of zero, what was needed? What was needed to think of zero, to invent zero? What was needed? And I'm saying in some sense that the kind of mind that is needed is one that is able to be mathematical at first and readily quantify nature as sort of a natural state of that person's mind, and at the same time have the transgressiveness that comes from art and comes from always drawing connections between the mundane and the spiritual. And it was minds, in a sense. I'm thinking that because it is such a trend, it doesn't come from just an establishment idea, right? It comes from a transgressive idea at the beginning. And in a sense, that has to come from an artistic leap, because unless you're being willing to have that artistic leap to understand that, oh, I have one, I have two, I have three, therefore I must have zero. It was, I think it doesn't stick. It takes courage to invent it in some sense. And so that's where that's one of the reasons why I told the story of René and sort of tried to give the insight that comes from this manuscript, this paper, because I think the way he thinks informs the way one might want to think about where zero came from. That's my suggestion, at least.
Right. I think you've hit the nail on the head, in the sense that we also think that zero may not have been invented within the system of mathematics itself, but that we have to look at the wider cultural context and the intellectual climate that prevailed at the time, and that could have been in any of the ancient civilizations. It could have been in Greece, it could have been in Egypt, it could have been in Mesopotamia, it could have been in China, could have been in India. And because no one has, to our knowledge, done such a systematic interdisciplinary study, we felt called upon to at least undertake the attempt. It might take generations before we be able to shed more light on the invention of zero, but we had to get started, and I think René agreed with that. He also realized how important zero was, and yet that so little is known about how it was invented. So I think that's true, and that's the process we're in, and we don't want to jump the gun and prejudice the project by singling out one particular society, one particular civilization. And that's why we have invited scholars from all these civilizations to put their heads together and compare notes to see whether we can come up with something that would be plausible. But I think what you said is right. I think we have to look at least in that direction of where these cultural antecedents overlap, because don't forget, in the old days, if you were a mathematician, you were also steeped in the classical tradition tended to be of your particular culture. And so you would be aware of, what's happening in the linguistic field, in the philosophical field, in the religious field. And it's that whole blend that could have, say, been the jumping off point for the idea even to occur. And without that, if it had just been mathematicians working only with math without in a vacuum, they may not have come up with zero. And we have a cognitive scientist on board who also comes to that conclusion independently of ourselves. That's why we invited him. And his take on it was that the brain functions in such a way that it registers stimuli, or at least processes the differences between stimuli coming in. And the challenge with zero is that it's the absence of any stimuli, and the brain is not trained to process the absence of stimuli. When the brain does that, it goes into a rest state, the neurons are quiet, and there's nothing happening. So how does the person, the brain, how does that lead to the conception that absence of stimulus may also be significant? And that's probably why it took tens of thousands of years for people to have performed mathematics across the world, going back as far as we know, tens of thousands of years, and then finally come up with the idea that zero could also be a number, could be considered a number. And not just considered to be another number, but to be the origin of all numbers. It's something that modern set theorists have also come to the conclusion that, that all the other numbers arise from zero. So zero, as it were, is the creative spot from which everything emerges and to which everything returns. And in that sense, perhaps it could be the still point, the balance, the dynamic balance that you're talking about. Which is also something that quantum physics is coming up with. The quantum vacuum is not empty at all. It's seething with particles coming into existence and being destroyed. Mm-hmm. So, that's why zero is so important, and trying to find or shed light on its origin is not simply an end in itself, but it's a means to a larger end to try to understand life. And I think that was René's quest, as it has been ours. So we're very grateful that René had the vision. Not everybody did at that time. We had approached other people, but René immediately accepted the invitation. And not only that, but in 2017, 2 years before his death, had we only known, René went to attend and open a conference outside of the Netherlands, which not everybody would have been inclined to do. So we're very grateful to René. Again, he had a large share in both the book project and the online event. And if only he could have been here. So thanks, Joe. Thanks, Thomer.
Thank you, Peter.
Until next week, when we are privileged to screen yet another world premiere, this time of an art exhibition by the Dutch visual artist, Miss Irma den Hertog, who will not be present on the occasion, but she will be present on the 23rd of January, when she will, she's also contributing an article to the book project, when she will discuss that article. Her painting, she's a visual artist, her painting, Void White, will grace the cover of the monograph. And we can reveal at this point that Irma's work is a deep dive into the pre-verbal experience of the void. So don't miss it. See you soon again, hopefully. And thank you all for joining.